And good evening, AP Physics students. Welcome to another example problem with Mr. Kirsten. Tonight I'm going to be doing as an example problem number 6 from chapter number 4. And again, the idea here is we're starting to deal with Newton's three laws. Newton's three laws, the fundamentals of dynamics. So problem 6 states, what average force is required to stop a 1100 kilogram car in 8 seconds if the car is traveling at 95 kilometers per hour? Okay, sounds like a lot of information going on there. Let's start in with our 5 problem solving steps. Okay, so I need to define a coordinate system, okay? Let's take our standard coordinate system with the plus x direction being to the right. I got my car, okay, and it looks like it is traveling to the right. I'm not going to draw an arrow just yet. Okay, I am going to next draw what's called a free body diagram. That is, I'm going to put a dot where the center of mass of my object should be, and then I'm going to draw in arrows that represent forces, and I'm only going to draw in forces. So this car must have some weight. Cars have mass, and if they're on the earth, they have weight. There's also a normal force. What is a normal force? That's the upward force exerted by a surface. The car has a weight, but yet it's not accelerating downward. Why is that? Because the surface exerts an upward force on it called the normal force. Normal literally means perpendicular, so a normal force is always perpendicular to a surface. And then there must be some type of force, we're not sure what it is exactly, but some force F that is causing the car to slow down. So the car is traveling to the right, but if it's traveling to the right, then it's slowing down. There must be some force acting to the left. So this is what's called a free body diagram. Notice no speeds, no velocities, no accelerations, only forces in that free body diagram. Okay, so I have a coordinate system, I have a free body diagram. We've got one of the 5 problem solving steps done. Okay, variables. Let's talk variables. Well, you know what? It may seem redundant, but let's just write out the things we know. A lot of times in a complicated problem, writing out the things you know will help you figure out what's going on. We know that the car is 1100 kilograms. We know that the time in question is 8.0 seconds from the time it's at some initial speed till the time it comes to rest. Speaking of that, the final speed of the car must be 0 meters per second. Final speed in the x direction is 0. The initial speed, VOX, is 95 kilometers per hour. 95 kilometers per hour. Now, I notice right away that I have meters, seconds, kilograms, but then hours and kilometers. This is not good. I'm going to have to do some dimensional analysis and convert this 95 kilometers per hour into meters per second. I'm sure you guys by now can do your dimensional analysis. Basically, we're going to multiply by 1,000 here and divide by 3,600, 60 squared, and it turns out 95 kilometers per hour is 26.4 meters per second. So this is my initial speed, and then my final speed is 0. Now I'm going to read the one problem one more time, and it wants to know what this force is. What is this force that's slowing it down? It wants to know the magnitude of this force. Okay, I want to know F. Well, that's all the information I know so far. Okay, well, there's only one equation we know right now that has force in it, and that is Newton's second law. force is equal to mass times acceleration. And this is a vector equation because the force and the acceleration must be in the same direction. Okay, so I want to know force. I know mass. I don't know acceleration. If only I could figure out the acceleration of this car, I would be in business. But I don't know acceleration. Okay, well, this is dynamics, but dynamics also deals with kinematics. So I could go back to chapter 2 here and try to find out what my acceleration is. So if I go and look at my equation sheet, I find that final velocity has to be initial velocity plus acceleration times time. And I see that I know every variable in this equation except acceleration, which I want to know. So if I do a little algebra here, I could find out that my acceleration should be equal to my final velocity minus my initial velocity divided by time. So plugging in my numbers here, I would get 0 minus 26.4 divided by 8 is equal to A. Or just writing that neatly here, I would get A is equal to negative 3.3. Now this is 26 is meters per second, 8 is seconds. So the units there is meters per second, which we typically write as meters per second squared. Now, notice algebraically there is a negative sign here. What does that mean? That means that the acceleration should be in the negative x direction or pointing to the left. Does this make sense? Yes, if I'm traveling to the right and slowing down, my acceleration is back the other way. So it is pointing in the acceleration should be pointing in the negative x direction. Notice acceleration and force point in the same direction. This is a vector equation. The net force, or sum of all forces acting on an object, always points in the same direction as the acceleration. Now the vectors are not identical. They point in the same direction, but I have to multiply the vector acceleration by the scalar mass to get the vector of force. So the net force equals mass times acceleration. Notice here the normal and the weight cancel each other out. That is, they are equal in magnitude in opposite direction. So the acceleration must be in the direction of the net force, or in the direction of this force F. Okay, well, what is the magnitude of F? Well, we now know our mass. We now know our acceleration. We can get to work here. So the net force is equal to just this force F. In other words, F is equal to the mass, 1,100 kilograms, times the acceleration, negative 3.3, okay? And then we see that this force is equal to a negative, what would this be? 3,630. And what would my units be? It would be kilograms meter per second squared. Kilogram times meters per second squared. Well, another name for that is a newton. A newton is the force needed to accelerate 1 kilogram at an acceleration of 1 meter per second squared. And notice this is a negative, once again indicating that the force is to the left, pointing in the negative x direction. Now, if you look in your answer book, if you looked at the answer book, the answer it gives is negative 3,600 newtons. What's going on there? Well, that is simply a significant figure thing. Again, don't get too worried about that. But 8.0 is two significant figures, 11.0 is two significant figures, 95 is two significant figures. So our answer should have two significant figures. Again, if that doesn't make sense, don't worry too much about it. Either answer would be correct. I always like to say what my force is and leave it like this, but just for emphasis, you could note the force is in the negative x direction, or the opposite direction of motion. Again, the question's asking, what's the force? Well, force is a vector, so when in doubt, you should always give a magnitude and a direction whenever a question asks for something about a vector quantity. So the net force here is 3,600 newtons in the opposite direction of motion. And that is the answer then to problem number 6. Thank you, physicists, for tuning in. And as always, we have a nice little reward for you for listening to my voice online. And the reward today is, something very epic. That's right. This is an old yearbook from Jefferson High School. And if we look very closely, we will see a very handsome individual in front of a very high-tech computer. Notice this individual has very long, flowing, beautiful hair. Apparently, this is a page about the post-secondary challenge. So there we go. There's your picture from the Jefferson yearbook a few years ago. So thanks, physicists. Have a good night. We'll see you in class tomorrow.